Friends, today we will discuss the topic complex numbers. Consider the equation x square plus 16 equal to 0, that is x square equal to minus 16. Solving this equation means finding a number x whose square is minus 16. Clearly, x cannot be a real number since the square of a real number cannot be negative. That is, we cannot find a real number whose square is minus 16. In order to overcome this problem, we have to introduce a new type of numbers. Root minus 1 is a non-real number. Let us denote it by the symbol I and call it the imaginary unit. Thus, I equal to root minus 1 and hence I square equal to root minus 1 into root minus 1, that is minus 1. We have I into 0 equal to 0 into I equal to 0. We have plus minus 4i square equal to 16i square equal to 16 into minus 1, that is minus 16. Hence, the equation x square plus 16 equal to 0 has two solutions, 4i and minus 4i. The numbers like 3i, I root 2, minus 5 upon 7i, etc. are called imaginary numbers. In general, if a is a non-zero real number and I equal to root minus 1, then the number ai or ia is called an imaginary number. Complex numbers. Consider the quadratic equation x square plus 4x plus 8 equal to 0. Then x square plus 4x plus 4 equal to minus 4. That is x plus 2 bracket square equal to 4i square, as I square is minus 1. Therefore, x plus 2 equal to plus minus 2i, that is x equal to minus 2 plus 2i, or x equal to minus 2 minus 2i. Thus, the equation x square plus 4x plus 8 equal to 0 has two solutions, minus 2 plus 2i and minus 2 minus 2i. Clearly, these are not real numbers. Such numbers are called complex numbers. Definition: a number of the type a plus ib or a plus bi, where a and b are real numbers and I equal to root of minus 1 is called a complex number. If a plus ib is a complex number, then a is called the real part and b is called the imaginary part of the complex number a plus ib. We note that the real part and the imaginary part of a complex number are both real numbers. I repeat, imaginary part of a complex number is also a real number. The set of complex numbers is denoted by C. A complex number whose imaginary part is 0 is a purely real number. Thus, every real number can be considered as a complex number whose imaginary part is 0. A complex number whose real part is 0 is called a purely imaginary number. Thus, 7i minus half I are purely imaginary numbers. Now we discuss equality of complex numbers. Definition is: two complex numbers a plus ib and c plus id are said to be equal if a equal to c and b equal to d. Thus, two complex numbers are equal if and only if their real parts are equal and also their imaginary parts are equal. If a plus ib equal to c plus id, then a equal to c and b equal to d. This is called equating the real and imaginary parts separately. From the above definition of equality of complex numbers, it follows that if a plus ib equal to 0, then a plus ib equal to 0 plus I into 0. Therefore, a equal to 0 and b equal to 0. Thus, a complex number is 0 if both its real and imaginary parts are each 0. The next part is addition and subtraction. Addition of two complex numbers is defined as a plus ib plus c plus id equal to a plus c plus I into in bracket b plus d. Here we add the real parts and the imaginary parts separately and get their sum. We can extend this rule for getting the sum of more than two complex numbers. Negative of a complex number. Let z equal to a plus ib be a complex number. Then a plus ib plus minus a minus ib equal to 0 plus I0 equal to 0. This shows that minus a minus ib is the additive inverse or negative of the complex number z equal to a plus ib. We denote it by minus z. We know that subtraction in the set of real numbers is defined as if x and y are real numbers, then x minus y equal to x plus minus y. Similarly, we define subtraction in the set of complex numbers as a plus ib minus c plus id equal to a plus ib plus in bracket minus c minus id. That is a minus c plus I into in bracket b minus d. The next part is multiplication. But before defining multiplication of two complex numbers, we consider the powers of the imaginary unit I. I square equal to minus 1, I cube equal to I square into I equal to minus 1 into I, that is minus I raised to 4 equal to I square square, that is minus 1 square, which is 1, I raised to 5 equal to I raised to 4 into I, that is 1 into I, that is I raised to 6 equal to I raised to 4 into I square, that is 1 into minus 1 equal to minus 1, and so on. In general, I raised to 4n equal to I raised to 4 raised to n, that is 1 raised to n equal to 1, I raised to 4n plus 1 equal to I raised to 4n into I, that is 1 into I equal to I raised to 4n plus 2 equal to I raised to 4n into I square, that is 1 into minus 1, that is minus 1, I raised to 4n plus 3 equal to I raised to 4n into I cube, that is 1 into minus I, that is minus I. Now we define multiplication of two complex numbers as a plus ib into c plus id equal to a plus ib into c plus a plus ib into id. On simplification, we get ac minus bd as the real part and ad plus bc as the imaginary part, and therefore the final product is ac minus bd plus I into in bracket ad plus bc. The next important concept is conjugate of a complex number. We have a square plus b square equal to a square minus minus b square, that is a square minus I square b square, that is a plus ib into a minus ib. Two complex numbers a plus ib and a minus ib are called complex conjugates of each other. A minus ib is the conjugate of a plus ib and a plus ib is the conjugate of a minus ib. Thus, to get complex conjugate, you have to change the sign of imaginary part only. It can be seen that the sum and product of two complex conjugates are purely real numbers. The next important part is division of two complex numbers. Let us try to divide the complex number 2 plus 3i by another complex number 2 minus I. This means that we want to express 2 plus 3i upon 2 minus I in the form a plus ib. Clearly, a and b are real numbers. we multiply both numerator and denominator of the quotient 2 plus 3i upon 2 minus I by the complex conjugate of the denominator, which in this case is 2 plus I. Then we have 2 plus 3i upon 2 minus I equal to 2 plus 3i upon 2 minus I multiplied by 2 plus I upon 2 plus I. On simplification, we get 1 plus 8i divided by 5, that is 1 upon 5 plus 8 upon 5i. This is in the form a plus ib, where a and b are real numbers. In general, if a plus ib is not equal to 0, then c plus id upon a plus ib equal to c plus id upon a plus ib multiplied by a minus ib upon a minus ib. On simplification, we get ac minus bd upon a square plus b square plus I into AD minus BC upon A square plus B